All right, let's get started. Whoops, why did that not switch over? We get started, but not adjusting. There we go. All right, so we're going to do something that probably is a review for most of you all, but we're going to change it up a little bit and start to do more of a differential equations approach or more of a time domain approach. We'll start off a little bit by something that you may or may not have seen in terms of writing a generic equation. And the key thing is the generic equation works for first order circuits, does not work for anything greater than first order circuits. When we get to greater than first order circuits, we're going to have to use a different technique to solve for that. So what are we going to do? We're going to solve for first order circuits, either RL or RC. We're not going to solve for LC or CL circuits. We're going to reintroduce tau, right, which is our time constant. We're going to come up with this generic equation to solve for any voltage or current in any system, and it's going to work for any first order circuit, voltage or current. We're going to look at time domain response, and we're going to come up with a concept of steady state. And we're going to look at switching intervals on some of the circuits. All right, so let's go. Now we're pros at writing KVL and doing loop equations. So what we see here is we're just going to write a KVL loop equation across this. Actually, not going to do a loop equation. We're going to do a nodal analysis equation to kind of make things a little bit easier. And what we see is, let's see, so here and here. So we know that the voltage drop or the current through a resistor is V divided by R, right? What is the current through a capacitor? One over C integral, right, of V dt, correct? And what we can do is we can sort of back calculate that thing and we can solve, and we can see that our derivative of IC is equal to 1 over C times V dt. So di C dt is going to be equal to essentially V over C, right? When we go ahead and set it up that way. And so when we go ahead and we solve our equations, we can write our generic equation, at least for solving a simple RC circuit. And notice there's no power supply in this, right? We're going to assume that the only energy that we have in here is perhaps stored in that capacitor, because otherwise it wouldn't be an electric circuit, right? It'd just be two elements that are in series with each other. And so this circuit has the equation dV dt plus 1 over RC times the voltage is going to be equal to 0. This is what we call a homogeneous equation, right? Set it equal to 0, homogeneous differential equation. And the problem is we've got an equation with the derivative of voltage plus the voltage as part of the solution. And if you remember way back in Calc 1, wherever you took it or whenever you took it, you know that if I take e to the x t, we'll just call it e to the xt. And if we take the derivative of e to the xt with respect to time, what do we end up with? Anybody remember that from Calc 1? No? It's just x ext, right? So to be able to solve an equation that has a derivative and the regular expression, we have to have a solution involving e to the something, right? It has to be e to the something for that to work for us. And so instead of actually solving the derivative of that, because we haven't had differential equations, and this is not a class on differential equations, we don't want to solve this with derivatives. We want to solve it with what we would call a generic approach for any first order circuit. Has anybody seen Laplace transforms? Have they done Laplace yet at all? Sounds familiar? Did you take diff EQs at SMCC? So you probably haven't seen Laplace unless you've done a differential equations course, because that's pretty much why we do Laplace, is to solve differential equations. So most likely, unless you took a circuit analysis course that was based, like a calculus-based circuit analysis course, you wouldn't have necessarily seen Laplace. But you were presented the basic of a time constant, right? Like everybody knows the time constant with DC, but somebody just waved their hands and just gave you the results. We're going to eventually develop how we can come up with the time constants when we look at circuits. So for now, let's just use that previous knowledge that tau is equal to RC. Your time constant tau is equal to RC in a RC circuit, or tau is equal to L over R in an inductive reactive circuit. Anybody know what the units of tau are or is? Yeah, seconds, because it's a time constant, right? So the units have to be seconds. And the nice thing that a time constant does, because when you actually come up with a solution, it's not written as a time constant. It actually, when you solve for it using differential equations or Laplace, you end up with the inverse of that. But using the time constant tells you or gives you an indication of how long something takes to reach steady state. So the bigger the time constant, the longer it takes for that system to reach steady state. And what I mean by system to reach steady state, meaning the system is fully charged or perhaps even discharged. Okay, that's the concept of a time constant. But it doesn't tell you a whole heck of a lot about how we start and how we end. So let's define a couple of cases. We're going to define y of 0, and we just call it y because it could be voltage or current. So we're not going to say v of 0 or I of 0. We'll just call it y, and then you can substitute v and I as necessary. And then your y of infinity is going to be your final condition. That's what it means when we get to steady state. If the time has elapsed long enough, which theoretically means an infinite amount of time, then you achieve your final condition. And one thing I will add, so we say y of 0 here. We got to define y of 0 a little bit, okay? There's a y of 0 plus and a y of 0 minus. The y of 0 minus is just before a transition, and the plus is just after a transition. Okay? And what do I mean by a transition? A transition is usually meaning that the circuit gets energized. A switch gets closed. A switch gets opened. A power supply gets turned off. Any time when you're changing the circuit by taking something in or out would be considered a transition. So here's our final equation, which has y of t for any time that we're trying to solve for. Our y of t, which again is our voltage or current, our y is our voltage or current, that's going to be equal to our final or steady state condition plus our initial condition, and notice it's just after the transition has occurred, minus the final condition, and then we multiply the expression, not the y of infinity, the initial one, but the y of 0 plus minus y of infinity. We multiply that whole thing by e to the minus t over tau. And why do we multiply it by e to the minus t over tau? Because if I want to solve for y of 0 plus, that's y of infinity. So if I'm looking at y of 0 plus, I can essentially put in time equal to 0, right? Because t is equal to 0. When e is raised to the 0 over t power, what is that another expression? How would you reclassify that? Or how would you say that? No? Luke? E to the minus 0 is what? Or e to the 0? It's 1. Anything raised to the 0 power is 1, correct? So my y of 0 plus is equal to y of infinity plus y of 0 plus minus y of infinity. That whole thing times 1. These terms cancel, and doesn't that make sense that y of 0 plus equals y of 0 plus? Right? So then the next thing is the y of infinity. What happens at y of infinity? So y of infinity equals y of infinity plus y of 0 plus minus y of infinity e to the minus infinity over tau. What is e to the minus infinity equal to? 0. Because e to the infinity is a really big number, but e to the minus infinity is an infinitesimally small number, 0. So y of infinity equals y of infinity plus y of 0 plus minus y of infinity times 0. That whole expression goes away, and we end up with y of infinity. So how did you come up with this generic equation? It's just by plugging and chugging. It literally is by plugging and chugging. This part, though, I should say over here, the e to the minus t over tau is because we need to solve the differential equation. And the only solution that will work for us is when we have that natural e term that we have raised to a power. All right. So let's assume that we have no external source here, right? And what we want to do is we want to go ahead and solve this generic circuit with no external source, but it does have an initial condition, and we want to write an expression for solving for the voltage across essentially the two elements. And so we know that V of 0 plus equals V naught, and V of infinity has to equal 0. How do we know that? How do we know that V of 0 plus equals V naught and V of infinity equals 0? Any ideas? It's not necessarily fully charged, but it does have some charge. But why is it equal to that initial charge value? Luke?
Because it's already what's on the circuit, and there's no additional force, so there's that way the
Sort of, but do you remember when we did the equations for capacitors? What'd we say? VC is equal to 1 over C integral of I dt, correct? And when you integrate something, you cannot get an instantaneous change. You can't go like that, right? You have to do something where it's like this. It decays slowly. So you cannot have an instantaneous change in voltage. So whatever voltage on that capacitor was there before you walked up to the circuit and started energizing it has to be the same as just after. So that's our transition we're talking about. So that's the first reason why we have V naught for our initial condition, or V of 0 plus. And the other reason why it goes to 0 is I got a capacitor feeding a resistor. Over time, that resistor is going to dissipate all the energy that's stored in the capacitor, until such time that there's no energy in the capacitor. If I wait a long enough time, that resistor is going to bleed that capacitor dry, and so that there's no voltage there. So that's why the voltage goes to 0. Move this out of the way. So what we end up with is our expression for V of t is equal to our initial condition, V naught, times e to the minus t over RRC. Pretty simple, pretty straightforward. All right, let's do this example. So we have a 9-volt source that we want to open the switch at time t equals 0. Okay, so that means we're taking the voltage source out of the system. It's just a 9-volt battery. We have a 2 ohm resistor and a 4 ohm resistor in the circuit. And the 4 ohm resistor is in series with a 12 microfarad capacitor. Okay. So we want to show, so you already know what your answer is. We want to show that the voltage is 320 millivolts at 200 microseconds. So what do we need to do? We need to write an expression for Vc of t, which is equal to Vc of 0 plus, of infinity, plus Vc of 0 plus minus Vc of infinity, e to the minus t over tau, right? That's the expression we're trying to solve for. So we got 3 things we need to solve for. We need Vc of 0 plus, we need Vc of infinity, and we need tau. All right? We need those 3 things. So the question is, what is Vc of 0 plus equal to? How would you solve for Vc of 0 plus? Any ideas? Is it 9 volts? I'm not arguing, I'm just asking.
I mean, maybe there's some voltage divider stuff we could do before.
Why isn't this there we go. So what's the best way to figure out what the initial condition voltage is? What do we know about capacitors in steady state? They can accept no more charge, can they? They're full. How would you represent a capacitor as being full and not being able to accept any more charge? An open circuit. So what I'm going to do, I'm going to say at t equals 0, just before the switch is transitioned, right? I've got my 2 ohm. I've got my 9 volt. I've got my 4 ohm, and I've got my open circuit. So this, by definition, is Vc of 0 minus. So what that tells me is no voltage drop across the 4 ohm resistor because I've got no current flow through there. So I know that Vc of 0 minus is going to have to be equal to 9 volts. And I know, because of what we just said, voltages can't change instantaneously in a capacitor, that has to be the 0 plus condition. Okay? That must be the 0 plus condition. No instantaneous changes in voltage. So that's why I need to know T at 0 minus and T at 0 plus, because T at 0 plus, that power supply is out of the picture, right? That's just after the switch's transition, where 0 minus, it's in the circuit, but it's completely, charged, it's fully charged the capacitor. So the first thing I've done is I've got Vc of 0 plus. Now I want to solve for Vc of 0 minus. So this is T, not 0 minus, of infinity. So this is 2 ohms. This is 4 ohms. And this is my capacitor. I'll show it as a capacitor. What happens to VC after a very long period of time? Yeah, it's fully discharged, isn't it? There's no energy source in there, but I have a way of discharging the capacitor through that 2 ohm and 4 ohm resistors. So it's going to, in fact, be 0. So I've got VC of infinity. Last thing I need is tau. How do I solve for tau? R times C. So which R and which C? I'll give you the easy one. The C, we know, is 10 mics. What is the R? 6 ohms? Why do you say that? I'm not saying you're wrong. I'm just saying why. Say more. What's a better way to say that? Sort of. I don't know if that's quite. I mean, yes, they do, but this capacitor is discharging, right? It's discharging through those 2 resistors. Aren't those 2 resistors the Thevenin equivalent resistance seen by the capacitor? So if I'm looking at this, that's what the capacitor sees, right? So all you're doing is solving for R Thevenin. That's all you're doing. So that's the other thing. When you want to solve for your time constant, you've got to know when you're looking for. I didn't care about the circuit at 0 minus. I cared about it in steady state because that's what the capacitor is discharging through. That's what that capacitor sees for resistance. So R Thevenin equals 6, and tau is 6 times 10 microfarad, which is equal to 60 microseconds. So my final equation, VC of t, is going to be equal to V of infinity, which is 0. Actually, let me write it out so you can see where I get the terms. This is V of infinity, or VC of infinity, plus VC of 0 plus minus VC of infinity times e to the minus t over tau. Now I'm going to plug in my results. 0, 9, minus 0, e to the minus t over 60 microseconds. So my final expression is 9 e to the minus t divided by 60 microseconds. Okay? Questions on that? Make sense? Don't make sense? So if you remember the problem, it said check what the voltage is at 200 milliseconds, or was it 200 microseconds? Let's see. 200 microseconds. So let's take advantage of MATLAB. And so we're going to write an expression. But first, we'll specify the time. So 200 microseconds is 2 e to the minus 6. So that's 200 micro. So our VC of expression, that's going to be equal to 9 times E, which is just EXP in MATLAB, to the negative T over tau, which is 60 e to the minus 6. $321 millivolts. Which checks our result. right? Everybody see how to solve that? Enter that in their calculators, do that process. Because that's exactly what you'll need to do when you solve this. If we go back to the PowerPoint, I actually showed you, right, all the initial conditions and the final conditions. If you don't like this, you could call this VC of 0 minus circuit and the V of infinity circuit. I even said V of 0 plus is equal to 9, but that's also the same thing as V of 0 minus. So after the switch is transitioned, here's my time constant, 2 times plus 4 times 10 microseconds equals 60. And here is my expression. To solve for the current, that's a little harder. Why is it harder to solve for the current than the voltage? So let's say we want to write an expression for for current here. What would be different? The current can change instantaneously in a capacitor, can it? Right? Because it's C dV dt is the current. So what I need to do is I need to go and I need to write an expression for, I need to figure out what the circuit looks like at T 0 minus, what it needs to look like at 0 plus, and what it needs to look like infinity. The reason why I need the 0 minus is because I've got to figure out what that initial voltage is on that capacitor, right? I need to figure out that circuit. So I still have to do this part over here. Then I've got, and I don't care about, I don't care about the current. I care about the voltage. Now I can calculate the current over here. Okay. So my 0 plus circuit now looks a little bit different, right? I didn't actually calculate a 0 plus. I did a 0 minus. So my 0 plus circuit becomes this. Here's 2. Here's 4. And that capacitor gets replaced with a 9-volt power source. Oops. I was saying volts, but I shouldn't have been talking about time. So now I can solve for the current through here. And the current, hopefully you see, IC of 0 plus is equal to 9 over 6 amps. And then I know from looking at this circuit, it's got to be equal to 0 because the circuit's completely discharged. The time constant is exactly the same. I don't have to do that step over again to figure out what the time constant is if I'm doing voltage or current, because that's just the rate at which the capacitor discharges. So now I can write an expression for IC of t, which is going to be IC of infinity, 0, plus IC of 0 plus 9 over 6 amps, minus IC of infinity, e to the minus t over 60 micros. So my current here is 9.6 e to the minus t over 60 microseconds. So I actually did the current calculation for a very specific reason. And the very specific reason why I did that is because I wanted to show you how much more work is necessary when you're solving for a parameter that can change instantaneously. In the capacitor, that's the current. So if you can simplify your world and just solve for the term that can't change instantaneously, in this case of the voltage, we had one less thing to solve for, right? Over here, we have to do that additional thing because the current can change instantaneously. Does everybody understand that? It's a subtle thing, but it's a lot more work. All right. So just be mindful of that when you're trying to tackle these problems. So here is it kind of formalized with doing the current calculation. Here is the time constant. Here's the voltage. The current is actually up here as well. And then I just showed you how to solve for that. So way that I did this is I actually showed you the math because this is a pretty good one to see. We actually plugged in 200 microseconds into the equation for T and ended up with 321. But if you want to solve for how long it takes, this is the approach that you do. So you take 9 e to the minus t over 60 micro, set it equal to 321 milli. You divide both sides by 9, right? And then I just went ahead and showed you when I put e to the minus t over 60 micro, and I actually show it as not a negative term, but a positive term, I end up with 1 over that expression. Then I invert everything, right? So this moves up to here, and these two swap positions. So what you end up with is e to the t over 60 micro is going to be equal to 9 over 320 millivolts, right? Now I take the natural log of both sides to get rid of the e term. So the natural log of 9 divided by 321 milli is going to be equal to t over 60 micro. Multiply both sides by 60 micro, and I get 60 micro times natural log of 9 divided by 321 equals 200 milliseconds. I'll show you how to do that in MATLAB. Again, you can just do this in your calculator. So 60 micro is 60 e to the minus 6. Multiply that by the log, which is natural log, of 0.321 divided by 9. And, whoops, 60 micro. Why do I have a negative 200? I shouldn't have a negative, I should have a positive 200, but why do I have a? No, that is the log is the same thing. In MATLAB, log is natural log. Oh, it's because of this. Whoops. It's 9 divided by 0.321. There we go. I had it backwards. Okay? Because you shouldn't end up with negative time, right? That doesn't make any sense. So that's how you solve these. If you want to actually solve for a specific time, like if you're designing a senior project and you've got an RC circuit and you want to figure out, hey, how long is this going to take for this thing to charge to a certain value or discharge to a certain value? You can go ahead and calculate that. We did a 555 timer in EET324 this week, which had a resistor capacitor connection. Excuse me. And I didn't actually teach them how to calculate charge and discharge, but that's what we basically explain, which is you ramp it up and you ramp it down, and how long it takes to charge is when that flasher circuit. So the whole timing on a 555 timer is based on how quickly that capacitor charges up to a certain threshold voltage to turn the output either on or off. That's all it is. And here's what it looks like. If you were to plot it out, you start out at your initial condition, and I've normalized it over here to show that it's V divided by V naught. So to make it unified to start at 1. And then as you can see, as time increases, it gets closer and closer to 0. But interestingly enough, it never gets to 0. So theoretically, you never fully discharge that capacitor if you have a resistor, because it will still continue to dissipate energy. All right, let's do a similar thing for an RL circuit. And an RL circuit is the same simple circuit. It's a simple RL circuit. And we're gonna write our differential equation. And we're gonna solve for our voltages here. So our equation is di dt, the derivative of I, plus I has to equal 0. Okay? Got to equal 0. So the only solution that is valid for this is when we have an e to the something t for its solution. So our generic approach, which is the y of t equation, that generic equation, is going to allow us to solve RL circuits, simple RL circuits. The difference is, right, what can change instantaneously in an inductor? Voltage can change instantaneously in a voltage. The current cannot. So what you need to do is calculate your initial condition for current. And then if you need to solve for voltage, go ahead and solve for the voltage and do it that way. So it's kind of the same approach that we did for capacitors, but you're just solving for different parameters. How about I give you 5 minutes to do this? 5 minutes. It's 10:05. I'll give you to 10:10. See if you can solve an equation for voltage, right? So that's a voltage across not the inductor, but the 40 ohm resistor, and see if you can come up with that equation. Again, do the process. Solve for your initial current because the switch is being opened at t equals 0. Solve for the current. Then, so that's the t equals 0 minus. So I'll write it out. Do the t equals 0 minus circuit. Do the t equals 0 plus circuit. Do the t equals infinity circuit, and solve for tau. So you have one additional step to solve for this. I'll give you to 10:11 because I've been yapping. So I'll give you 5 minutes. I'll pause the recording too, unless people have questions. This doesn't waste processing time. but I can still oop, that's not my, I'm gonna pause the recording. All right. What'd you get? The right answer? How do you know? You didn't get negative 12.99? What'd you get? Okay. Anybody else? Get a different answer? I'm not sure where to go. So let's do the process, right? Because we need to solve for voltage means we need to solve, no matter what, we need to solve for that initial condition current. So that's regardless of whether you're solving for voltage or current in an inductor or a capacitor, you need to solve for the zero minus condition. And in the zero minus condition, what happens to my inductor? What does an inductor become? Becomes a short circuit, right? So my IL of zero minus is going to be equal to 24 volts divided by 10 ohms, which is 2.4 amps, is it not? Isn't that my steady state current if it's the inductor has been allowed to charge for a very long period of time? So I end up with 2.4 amps. Now, because I'm looking for voltage, I need to solve for my zero plus circuit. And my zero plus circuit now has that power supply out of the circuit, but that has been replaced by a current source, isn't it? And the magnitude of the value of the current source is 2.4. What's the direction of current? Is it arrow pointing up or arrow pointing down? Right, because that's what I need to know with a voltage source. I need to know, I mean, a current source, is the current going up or is the current going down? So which one is it? Down. Because it was down when it was steady state, isn't it? At the zero minus one. So now, what is VL of zero plus going to be equal to? Or not VL, sorry. V40 of zero plus, because I'm not looking for the voltage across the inductor. I'm looking for the voltage across the 40 ohm resistor. So what is VL of zero plus or V40 of zero plus going to be equal to? Shouldn't be hard. Isn't 2.4 going that way? So that is a plus to minus drop in that direction. And since I'm looking for that voltage there, which has the opposite polarity, that's going to be equal to a negative 40 times 2.4, which is 96 volts. Is that correct? I believe it's negative 96. 40 times 2.4, I think is 96. You can check me if I'm correct, but I think it's correct. That's correct? Okay. So that's my first voltage. So I had to do that T of zero minus just to get the initial condition. Then I still had to do the zero plus condition. And notice I didn't solve the zero minus for the voltage because it's already zero. I know what it is. It doesn't matter. But I needed it for zero plus because I can get an instantaneous change in voltage, which now means I'm ready for my T equal to infinity circuit. What happens to my inductor at infinity? It's completely discharged, right? Current is zero. How would you show current zero? Do I put an open or a short circuit there? Open circuit, right? So what is VL of infinity equal to? Better be 0 volts because there's no charge mechanism whatsoever. So I've got 0 minus current. I've got 0 plus voltage. I've got L or T of infinity voltage. Now I only need my time constant. And what should I use for my time constant? Remember all the way back at the beginning, when we talked about setting up circuits, we had our expression that tau is equal to L over R, correct? So what is L and what is R in this circuit? L is pretty easy. It's equal to 5 Henry. What's R equal to? What is it? 50 ohms. It's the same thing. It's R Thevenin. It's what the effective resistance is seen by the inductor. So it's just R Thevenin. In this case, that is times 50 ohms. So my time constant is 250 seconds. So my final expression for VL of T is going to be equal to VL of infinity plus VL of 0 plus minus VL of infinity e to the minus t over tau is going to be equal to minus 96 plus, minus 96, it's 0, got it backwards, sorry. 0 plus negative 96 minus 0 e to the minus t over 250 seconds, or VL of t is equal to negative 96 e to the minus t over 250.
L over.
Oh, L over R, yeah, not L
Or
times R.
50.
Sorry about that. Math is not very good. My math is good, actually. It's just my equation wording is not very good. So that's going to be equal to 5 divided by 250, which is, what's that?
5 over 50.
Oh, 5 over 50, yes. So 110. So not 250, but 110 or 0.1. So the question was, show that the voltage equals minus 12.99 at 299 milliseconds. We can certainly plug in our value. We can also say negative 96 e to the minus t over 1 is going to be equal to negative 12.99. We divide both sides by negative 96. E to the minus t over 0.1 is negative 12.99 divided by negative 96. So the negative signs will cancel. Then I'm going to invert. So I have e to the positive t over 0.1 is equal to 96 over 12.99. Take the natural log of both sides, and I have t over 0.1 is equal to the natural log of 96 over 12.99. Then I multiply both sides by a tenth. And that's my time. Let's plug that in. All right, so 0.1 times the log of 96. I should put that over here, actually. 96 divided by 12.99. And I get 2. Why is it saying 2 and not? It's 2. No, it's 96 divided by 12.99. I think I got that right. Here, let's see what we have over here. That's my current. Oh, Nobody corrected me. I said 40. Oh, wait a minute. 40 times 2.4.
No.
No. Take a look. So I did this wrong in the notes. This is the voltage, right? I'm not interested in VL. I'm interested in V. So I solve for VL and not V. So if this was VL, I would get that value. But if this is V, then it actually is 200 milliseconds, right? Which makes sense because the voltage drop across the 40 ohm resistor is going to be slightly smaller than the voltage across a 50 ohm resistor. So that should have been 200 milliseconds. Okay. So I did that approach for that, but you can take a look and you can see what the results are. Questions on how to do that? Because it's the same approach. You're just solving slightly differently. Am I doing this one first or the next one first? And again, you can see the current starts out at its initial condition, and then it decays over time, and it happens to reach about 37% after what we call one-time constant. And one-time constant means T equals tau. So when I plug in tau over tau, I get e to the minus 1. And e to the minus 1 is equal to what? 36.8 or 0.368. You can take a look here in MATLAB, but log of minus 1. Oops. Log of, why am I getting a J term? So e to the minus t, actually, I don't do log, I just do e. Sorry about that. That's what I'm doing. It's just exp of minus 1. So 36.8% of it is left. 63% or so has disappeared. All right, so if the circuits get more complicated, no big deal. You're just solving for R Thevenin. And you're solving for R Thevenin looking outside of there. So if I'm looking at this circuit here, what I see is I have, this was R1, R1, R2, R3. I'm looking externally. Kind of ugly to look at it that way, right? So I'm going to change the circuit a little bit and make it a little easier to see. I know that I need to go to R2 from this terminal, and then R2 is connected to R1, which goes back to that terminal, and R3, which goes back to that terminal. So if I'm looking for R equivalent for that circuit, it's a little easier to see. What I end up with is R equivalent is equal to R2 plus R1 in parallel with R3. It's always what or how hard does the capacitor need to work to discharge itself or to charge itself, either one. Okay. Same thing with the inductor. You're going to open this up and you're going to draw the circuit. So let's go back over here. And I have a resistor here. That's R1. That's R2. R3. My inductor is here, opening it up. And this, I believe, is R4. So now what I'm going to do is I'm just going to basically expand it. R3. This is my terminal. My other terminal is over here. And here is R4. So hopefully what you see is R equivalent is equal to R3 plus R1 in parallel with R2 plus R4. Okay, because that's what the inductor needs to do to be able to discharge itself. Those are the resistors. That's the equivalent resistance it sees is the Thevenin equivalent. So I think we kind of summarized this pretty well, but just to summarize here, voltage can't instantaneously change in a capacitor. So the T0 minus voltage is the same as the T0 plus voltage. Resistor voltages, though, in a capacitor circuit, those can change instantaneously. No doubt about it. All right. But once you transition your circuit, they will follow whatever pattern, which is our natural response pattern as shown, e to the minus t over 10. All right, I'll give you 5 minutes. 5 minutes. Solve for I1 and IL. I'll pause the screen recording and we'll go from there, unless there's any questions on how to do this problem. The only thing, maybe I'll add, the only thing is your tau, okay? Your tau has to be L times R Thevenin. This is going to be the equivalent L for those inductors. All right? That has to be the equivalent L. Yes, sir.
The L equivalent over R Thevenin.
Oh, L equivalent. Why do I keep saying that? Yes. L equivalent over R Thevenin, not L times R. Yes, sorry. All right, I give you 5 minutes. Godspeed. I just want to add too, because you're solving for currents in an inductor, you're solving for I1 and IL. You want to solve just for the circuits, T of 0 minus, T of infinity, and tau, because that current can't instantaneously change. So I'll pause the recording again. All right, for those of you who are diligently working, keep working. I'm just going to go ahead and put up what or how I would tackle the problem. So I know the inductor current has to be not changing. So I need IL of 0 minus. I need IL of infinity. And I need tau, correct? Seen by that inductor. This current here is through a resistor, right? That current can instantaneously change, can it? So I need I1 of 0 plus I1 of infinity, and also tau seen for that circuit. And we'll see if those taus are different or not. So we'll start off, in all cases, you need to solve for your initial conditions. So we'll start off with 0 minus. So I'm going to go ahead and just put this as a 180 ohm resistor. Let me know if anybody has any heartburn with that. This is 18. Oops. This is a short circuit because there's no more changing current, right? There's no voltage developed. I have a resistor. I have a short circuit. And I have another short circuit. And I'm looking for that IL right there. So what I see is I see that 18 volts is going to be across the 50 ohm resistor, right? And that's the current IL. So IL of 0 minus is going to be equal to 18 volts divided by 50 ohms, right? Now I need to do a T equals 0 plus only because I need to get what that initial current is for I1 because the current can change instantaneously in a resistor. So now I'm going to redraw my circuit. This is 180. My power supply is gone at this point. I have 90. My current through here is going to be an ideal current source. And I'm going to show these two as current sources. But the current that flows through there is going to be shared between them. And it's not going to be shared equally. It's going to be shared based on these ratios, right? Like you can do current divider through inductors and then basically just do the current divider and calculate what that'll be. So more current will be going through this one. You can find that by going 2/5 times 18/50, and the rest has to go through, whoops, the other way around, 3/5, because I'm doing current divider. So the current has to be equally shared. But what more important is that current 18/50 is flowing back in here. So some of the current goes through here and some of the current goes through here. So my I1 of 0 plus is going to be equal to 18/50. And this is current divider. So it's multiplied by the one not of interest by the sum of those, right? What is that? 2/3? So let's see. So that's 18/50 times 2/3. That becomes 25/1. That becomes 6/1. So that's, whoops. I'll stop it. That becomes 6/25. That's my I1, not IL, but I1. Why do I keep writing L? That's I1. Now I need to do my T of infinity for both circuits. What's T of infinity going to be equal to for IL? 0, right? The inductor is fully discharged, which also means I1 of infinity is going to be equal to 0. Now the only thing I need to do is get my time constants. So my time constant, let's see, for the inductor, right? So I know that I've got that inductor, that inductor, that inductor. So I've got to solve for the combination of those. So let's see, I've got 1 millihenry, 2 millihenry, and 3. And so the L equivalent is just like, so inductors act just like resistors. So that's going to be 1 millihenry plus product over sum. If I added that up correctly. Now my R, so I've got to go back here and do what my R is going to be equal to. And again, I'm going to go ahead and look at the outside perspective of what I see. So I can pick any old inductor. I'm going to pick my I1 here. I've got 50 ohms, right? That's 50 ohms.
Oh,
Question, yeah.
Is that 11?
11/5. Right, I just did common denominator. So 11/5. So then I'm going to go ahead and I'll boy, this is not working at all. I'm going to go ahead and discharge through those two. So those have effectively no impedance. Then I've got 90. And 180. And my R Thevenin, and I'm not going to do this in my head. is going to be 50 plus 90 in parallel with 180. So, and that is going to be the same time constant for both circuits because the current flowing through the resistor comes from those two inductors. So it doesn't change. So my tau is equal to 11 over 5 millihenry divided by, yeah, I'm not going to do that in my head, 50 plus 90 in parallel with 180. So my IL of T is equal to, was it 18 over 50 amps, e to the minus T over the tau over here. And my I1 of T is going to be equal to 6/15 e to the minus T over tau.
Can you go back and explain the like the T equals 0 and then the plus?
Yep. So the whole thing about doing these problems, okay, the most important part is when you look at the circuit and you're relying on the initial conditions of the system after the circuit has transitioned. And so what I need to do is look for initial conditions that aren't going to change instantaneously. So what that means is I'm going to look for T equals 0 minus for the things that can't change instantaneously. In the case of the inductor, it's going to be IL, right? So I know T equals 0 plus, but that also equals 0 minus, that also equals 0 plus, okay? Then once I know what that current is, I can build my 0 plus because again, I can't change my circuit. So at T equals 0 plus, then I can solve for I1, not IL, but I1. And the reason I can solve for I1 only after the switch is transition is because the current can change instantaneously in an inductor, where it can't change instantaneously it can change instantaneously in a resistor, but it can't in an inductor. So I had to solve for that 0 plus case just for the fact that I was doing it for the resistor. Once I have those two, then I can solve for the T equals infinity case for both of those, because at that point, you know, the things are the same, right? The circuit isn't changing at that point. It's just basically completely discharged. So the hardest part about it is making sure you go through that process. So if you want to write the process, it's step 1, right? So find the T equals 0 minus non-instantaneous changing, call it element. Then step 2, and we'll put this as optional, right? Step 2 is find the T equals 0 plus for any instantaneous changing element. So the reason why that's optional is because you might not need to do it. Like if we didn't have to solve for I1, you wouldn't have to do step 2. Step 3, find the T equals infinity for all elements. If you need it, right? Voltage or current doesn't matter. Step 4, find tau using equivalence. And that means Thevenin equivalence as well as capacitive or inductive equivalence. And then step 4 is fill out Y of T equation. That's kind of how we would do it generically. The hardest part, right, is what's instantaneous changing So instantaneous or non-instantaneous. So for a capacitor, right, what changes instantaneously is IC. What doesn't change is VC. For an inductor, what doesn't change, what changes instantaneous is VL, and what doesn't change instantaneous is IL. In a resistor, IR and VR can change instantaneously. There's no energy storage in those devices to fight the changes. So you're stuck dealing with the changes. Right? So that's the way you kind of just generalize things. I am pretty much out of time. Did anybody go to SGC last night? You went on Tuesday. How was it?
They were talking about like the officer was like as they're working on that, I didn't realize it, like, we even have one in there. The answer.
Well, it's nothing, this is developmental, it's research based, but they are building some, well, there are some, they're not floating, but Block Island and Rhode Island, they have some there. So that's the first one in the US. But you go to Europe and they have a bunch more. But we don't have any floating ones in the US at this point. Get good Chinese food?
Those.
They give a lot, right? I mean, they probably tell you to take some home because for them it's $300. It's like the best deal because they get what, how many were in there yesterday? 20, 30 of you all, or Tuesday? Yeah, for that many people to show up, you know, it's a pretty cheap investment of some good Chinese food. So anyway, I'm way over time. So don't forget there's no class on Tuesday, right? You get fall break.
Could you just go back to that last problem we were doing?
I don't know if I have time to go. It's 10:48. We're 3 minutes over.
Yeah. Okay.
I'll have the video up so you can take a look, and if you have questions, we can.
I was gonna be curious how to set that up in that Y equation thing, but.
So all you're gonna do, the Y equation, it's generic, right? It's Y of infinity, which we know was 0 in both cases, plus Y of 0 plus minus Y of infinity, e to the minus t over tau.
And that Y can be either an inductor or resistor.
It's a voltage or a current.
On
it's a
certain-
Exactly. It's a voltage or a current on any of the circuit components except for the supplies.
Okay,
Right? Because a power supply, it's always fixed. It doesn't change.
okay.
All right. I'm way over. Have a great weekend and a couple days off. I will see you on Thursday next week. Take care, everyone.
Thank you,
Thank
Paul.
you.
It's all right, that makes up for the time you guys found.
Yeah. Arthur, Arthur, set up a meeting with me like right now. I'm going to walk down to my office. I'll be there a couple minutes early. Okay.
Yeah, I can do that.
Okay. I'll see you then.